Hello and welcome. In this video, we're going to look at another parallel power example. It says, given the following circuit where the 8-volt source is supplied to produce an 11 milliamp current flow, R2 is 3K and R3 is 24K, solve for the power in R1, right? They didn't give us power for anything. Right? They just gave us R2 and R3 values, and they gave us the voltage source, so we know a couple of things already. So let's write out what we know. We know that the current will divide through all of these branches. We don't really know how it's going to divide just yet, so we can't use that readily. But we do know 8 volts is going to be down each branch. So we know 8 volts down this branch, and 8 volts down this branch. And the goal here, to be able to apply any of our laws, is to find 2 values for each of our branches. And so in this case, we can say that we have 8 volts and a resistance value. So we can use Ohm's law. We can say that since we have voltage and resistance, we can find the current down that branch. And we need the current through the branch to get to the power down the branch. And so let's do that. Let's say that I2, the current down the second branch there, is equal to our 8 volts divided by the R2 branch value of 3,000. Right, 3 kilo ohms. We'll set that out and we'll solve that using our decimals. We'll say that we have 8 volts divided by 3,000 ohms. That gives us a really small current, right? So we'll say that that is, we'll move it over by 3, it's 2.67 milliamps. So now we know the current down that branch, we know the resistance down that branch, we can technically find the power down that branch if we wanted to, right? Next one, we can go for the I3 current. We can say I3 can be solved the same way. We have 8 volts on top. We know that that R3 is 24,000 ohms. So we can solve that out. We can say that we have 8 divided by 24,000. So at this point, we get 3. We'll move that over 1 to get it back into the milliamp. We'll say that we have 0.333 milliamps, right? Because it gave it to us to the -4. We need it to the -3. So moving that back 1 gives us 0.333 milliamps. And we want to match all of our milliamps together because we're going to use KCL. KCL says that we can subtract out what we know we lost down the other branches, and we'll be given what's left down that final branch. So now that we know all the current drops down the other branches, we can use our total current of 11 milliamps and subtract out 2.67 and 0.333. Right, we're left with a really large current down that branch, which means that that R1 resistor is probably pretty small in comparison to these other two. So our I1, the current down this other branch, I1, is equal to 7.997. Right, it's almost 8 amps, 8 milliamps, MA. So now that we have the current and the voltage down that branch, we can use that to find the power down that branch. We know that is back to our power law. We can say that power is equal to voltage times current. So P1 is equal to the voltage down that branch, 8 volts, multiplied by the current down that branch, 7.997 milliamps. So we'll send this out. Since we're multiplying a base number, 8 volts, by a milliamp value, if we leave it in milliamps, we're going to get a milliwatt output. So 8 multiplied by 7.997 gives us 63.976. We'll round that up to 64. So power 1 is equal to 64. And since it was in milliamps there, we'll put a milliwatts here. So keep in mind that if you are dividing the number, you really want to account for all the zeros in that milliamp value, because that is not going to be the same result as when we multiply these numbers. And so when you're multiplying, you can kind of skip some of that milliamps and kind of transfer it over. But when you divide, you need to make sure that you account for all those, like we did with the resistors in this example here. Okay, let us know if you have any questions.